So in this video we're going to hook up a RC series circuit and view the voltages using an oscilloscope. So I've got here a 1 kilo ohm resistor and a 0.22 microfarad capacitor. Okay. And then I have my function generator lead. So up here is my function generator. And I have this lead on here. This is just a coaxial connection on here, and this goes to the output. You need to make sure there's two inputs on this function generator. The top one is a synchronization signal to connect multiple devices up and have them synchronized. All right, you don't want to connect to the sync. You need to make sure that you connect to the output, so it's labeled output right up above there. And you just need to use a straight coax cable with alligator clips here. Alright, so this is just a straight feed through cable, and so we have the alligator clips so that we can connect the sine wave into the circuit there. Now over here I have the oscilloscope, and I have on the oscilloscope I have traditional oscilloscope leads. You need to make sure that you do not use the oscilloscope lead. You do not connect this to the function generator, because this actually has some circuitry in here, and it's going to have dramatic effects on your circuit because of the circuitry inside of these probes. So these are oscilloscope probes. So you connect them there. These are ×10 probes. So you need to make sure that you set your attenuation on the oscilloscope to ×10. Now this probe, this is a ground. There's a little alligator clip connection on here, which is a ground, and then this is the probe. Now the probe, you can slip off this plastic tip, and then it's just a pointy metal probe right there. Okay, really sharp, and that would be for probing into a circuit that you don't really want to connect to. You just want to measure some signals inside of a circuit there. All right, but if you put this little cap on here and click it till you hear it click, and now it actually comes through there, and there's a little it's spring loaded, and then you can come in there and you can actually hook it onto a section of lead or wire within your circuit. Okay, so this is the positive, and the alligator clip is the negative side of the scope probe. Okay, so we're going to connect this circuit here. So we're going to take our circuit here. This is our RC circuit that we had here in our previous lecture. So we had 5 volts feeding a 1000 ohm resistor and then a 0.22 microfarad capacitor. So we're going to wire this circuit up. Okay, so this is our voltage source here, and we're going to set this to 5 volts RMS, and we're going to connect it up to one side of the resistor. Now resistors don't have any polarity on them, so it doesn't matter which side you hook up. And capacitors, okay, this here capacitor actually has a polarity. You see the black stripe there? Those are got little negative signs on there. This is polarity for this capacitor. It's what they call an electrolytic capacitor, and it does have a polarity. However, the polarity only applies if you have direct current in your circuit. Alright, so in this circuit here today, I'm not going to be hooking up any direct current. It's going to be just AC alternating voltage the entire time, so I don't really have to worry about the polarity of it because I don't have any DC bias in there. but I'm not using that one anyhow. Now this particular capacitor, I believe this is a Mylar capacitor, and it does not have a polarity, so whether you're doing AC or DC, there's no polarity here. But so I'm going to hook the ground up to the one end of the capacitor, and then I'm going to take a little jumper here and just jumper the middle from the resistor to the capacitor. So I'm just going to jumper those together. And so there's my RC circuit. Here's my voltage source on the left, just like was shown on the screen on the circuit, right? And then the resistor, and then a little jumper wire, and then the capacitor, and then the ground returning the supply. So now what I want to do is I've got my oscilloscope here, and my oscilloscope has two channels. So I have two probes, one's yellow and one's blue. And so I'm going to take the yellow one is labeled channel 1, that's my primary channel. So I always like to make sure it's my reference. Alright, so I'm going to just hook that up to the voltage source. So I'm going to come over here, I'm going to connect this ground up here. So I'm going to connect the ground to the ground, and then I'm going to connect the high or the hot side to up to here, and I'm just going to press that in and clip that in there. And so now you can see on the oscilloscope, you see the yellow sine wave that is being displayed there. Now you also see that blue stuff. That's just because this probe is just out here, and that's just noise it's just picking up. Alright, so we have the sensitivity, the vertical sensitivity set to 100 millivolts, and it's just picking up a lot of noise there right now. Okay, but once I hook it up, you know, that noise will decrease dramatically, and so you probably won't even notice it there. Alright, so but again, on your probe, you've got a ground and you've got the positive side here. Now this ground is the same ground as the ground on the first probe, and so when you hook up an oscilloscope, you have to be extremely careful, because you can't connect a ground across some other point. Your ground is only one place in the circuit. Okay, so there's only one ground in the circuit. Okay, again, if you kind of look over here, right, you see the ground. Right here is our ground, and there's only one ground, and so you need to make sure that the grounds only hook up to the ground. So if you try to hook the ground up, say here to the middle, so we got our function generator here, and I'm going to go to the amplitude, and you see I've currently got it set to 5 volts peak to peak. So what I'm going to do is I'm going to enter in the number here. So I'm going to select the green button, enter number, and then I'm going to choose 5. So I'm going to put in 5.0. The green numbers are listed there to the left of the actual buttons. And then I want RMS, so I'm going to choose RMS here. So I'm going to press the RMS button. Alright, and so therefore you can see here on the function generator, you can see that it's 5 volts RMS. And so when you look at the sine wave now, the sine wave is off the screen again, so we need to adjust it. And I'm going to turn off channel 2 for a minute, so I'm just going to set channel 1 so that we can see the sine wave. And so remember, it's 5 volts RMS, and so the peak to peak value would be, okay, so 5 volts RMS times the square root of 2 would give us the peak value. And then multiply that times 2 to get the peak to peak. So we're actually at 14.14 volts that's the peak-to-peak voltage for a 5-volt RMS. And so if we were to look here, if I was going to measure this, now number one, I had to change my volts per division for channel 1. So I've changed that to 2 volts per division. And then what I'm going to do is I'm going to take the bottom and I'm going to put the bottom right on the very bottom edge of the screen there. And now I can count up, and remember I should be counting to 14. So if we count up here, we've got 1, 2, 3, 4, 5, 6, 7, and I'm going to actually kind of slide this over here so it's right on the middle of the line so that we can see that. So it's just a hair above 7 divisions, right? But 7 divisions times 2 volts per division is going to be 14 volts, okay? Peak to peak. So remember, you wanted to adjust your waveforms when you're trying to measure values. Don't be afraid to just shift it a little bit. The other thing is we want to set our frequency. Okay, so like right now I have the frequency is actually at 200 hertz. And so what I want to do, I'm going to turn on channel 2 again, and I'm going to adjust the magnitude of it a little bit. Now they look like they're almost the same. So remember, on our, I'm going to drop this down to 100 hertz, okay? And so I'm going to bring this over here, and I always kind of like to start the sine wave, so I'm going to start my reference point of the sine wave. I'm going to start that reference point of the sine wave there, so that the yellow is crossing. The yellow is my reference, right? That's my source, and that's my reference. So I want to put that so that it's going to start right at a grid mark, so I can clearly see that that's at a grid mark. And really what I'm looking at right here is I want to see, I'm looking at the phase. So you see that the yellow, that is our source voltage E, and the blue is the voltage across the capacitor. So we can see that the voltage across the capacitor is behind the source voltage. And that's that Eli the Iceman, right? So current in a capacitor is in front of the voltage. So we're seeing the voltage in the capacitor is behind the supply voltage, okay? And so that's what we're seeing. The blue is behind, it's to the right, it's coming later in time. Remember, time is moving from left to right on here. So the horizontal is the time scale, and it's moving from left to right. And so we can see this phase shift is behind. All right, and so what I'm going to do now is I just want to view this right now. So what I'm going to do is I'm just going to kind of come up here to my function generator, and I'm going to dial up the frequency. Okay, so as I dial up the frequency, you see more and more sine waves showing up, number one, but also notice the blue is getting smaller. Right, that the blue is the voltage across the capacitor. So as the frequency increases, the voltage across the capacitor decreases, and that's exactly what we calculated on our on the last video. We calculated that, and so if you remember here, I actually still have it in here in the computer. So the voltage at 100 hertz, the voltage across the capacitor was 4.95 volts RMS, which was, you know, the supply was 5 volts RMS, so they were almost identical. So if I scroll that, if I dial back down to 100 hertz, right, you see that the magnitude in blue is almost identical to the magnitude in yellow. Yes, there's some phase shift. They're not right on top of each other, but the magnitudes are almost the same because the capacitor is dropping all the voltage right now, or not all of it, but majority of it. But as I dial up, so if I dial up to 700, right, which is close to, 723 was that critical frequency, you can see that the voltage has dropped significantly. All right, and so what I'm going to do here is I want to try to measure the blue voltage, so I'm going to slide it down so that the blue voltage is starting on that first line. It's actually the first line above the very bottom. I like to, if I can, don't put it on the complete bottom. And so now notice that the blue is in volts, 2 volts per division. I don't know if you can read it very well on your screen there, but it's in 2 volts per division. And we're lined up here on this first line above the bottom, and I'm going to count up. So that's 1, 2, 3, 4, and then I'm going to shift it over a little bit so we can see. So it looks like it's about 4.5. So that is about 4.5 divisions. So we're about 4.5 divisions. And our voltage is 2 volts per division. So the divisions cancel out, and we're going to be left with volts. Now remember, so that gives us about 9 volts. So that's about 9 volts peak to peak. All right, so that's the Alright, so let me line this back up here. Alright, so the reference is the center line, and I'm going to dial this back down to 100. Okay, so at 100 you can see that the voltage, the blue voltage is almost the same height as the yellow. So the magnitude is about the same because we're dropping 4.9 of the 5 volts RMS across the capacitor at 100 hertz. But as I dial up the frequency, as the frequency goes up, you can see we're getting more and more sine waves on the screen. But you see the blue sine wave is getting smaller and smaller and smaller and smaller. That is the frequency response of that capacitor. The impedance, or the capacitive reactance, which is impeding the current flow, is decreasing, and so the capacitor is not dropping as much voltage. So if I dial back down, right, we can see that the capacitor is dropping all the voltage now. But as I dial the frequency up, the frequency goes up, the impedance of the capacitor goes down, and so the capacitor is not dropping as much voltage, which means more of that voltage is being dropped across the resistor circuit in there. And so we can see that decay. The other thing that we can see if I change my scaling is you can see the phase angle. You see how far behind the blue is now compared to the yellow? They're way further behind because there's more phase shift also. So there's more phase shift going on. So let's try to measure our phase shift. Okay. Before we measure the phase shift. I'm gonna go back down to 100. So I'm gonna start at 100. Okay, so here you can see I've got my one sine wave here. I've got the yellow, which is the supply voltage, and it's my reference, and so I've got it lined right up here. I've got it lined up so that the yellow is crossing right at this grid point. And then we have, I don't have quite one complete sine wave on here, okay? So you can see there, it actually might be one complete sine wave, but it's not quite fitting on the screen because it's falling down there. So what I might want to do, depending on the scaling of your waveform, you may need to adjust that a little bit. So I'm going to line it up here. I normally don't like to line it up right there at the very edge because it's hard to tell whether you've captured it. All right, and so, but I'm just doing that to see if I have one complete cycle. And it looks like I'm just shy of one complete cycle there either way. So what I'm going to do is I'm going to change my scaling for the time so that in this case I'm getting two waveforms. And I'm going to turn off channel 2 for the moment so that I can just measure the time, the period of this waveform. So remember, the period of the waveform is how long it takes to make one complete cycle. So I'm going to line it right up here. So this is the start of the cycle right at this grid point. And then I'm going to count over. From there, I'm going to count over divisions. So I have 1, 2, 3, 4 divisions. And it looks like it's actually just slightly more than 4 divisions, but we'll just call it 4 divisions here. So we have 4 divisions, and then we look at our time, and our time is 2.5 milliseconds, 2.50 milliseconds per division. So the divisions cancel out, and you're left with 10 milliseconds for the period. This is the period T, and so therefore the frequency is 1 over 10 milliseconds, which is going to be 100 cycles per second. Okay, so give or take a little bit of round off there, you can see 4 divisions times 2.5 milliseconds per division is 10 milliseconds, and then the frequency is 1 over 10 milliseconds, which is 100. I wrote cycles per second, but the correct term for that is hertz. Okay, so 100 hertz, which is what the function generator is telling me I'm at, but it's good to verify on the oscilloscope. Okay, so we've got 100, one complete cycle then. One complete cycle is 100 millihertz, or 100 hertz, okay, or the time is 10 milliseconds. So now what I'm going to do is I'm going to turn channel 2 back on, and what we want to do is we want to measure the time between the yellow and the blue. And now when you do this, I changed the scale, okay, so you see as I change the scale, and so you want to change a time scale so that you can spread them out further. The further you can spread them out, the more accurate it's going to be. But now they're going, now they're going really at an angle there. So what I'm going to do is I'm also going to scale it. I'm going to scale the vertical so that they look like they're going more straight up, okay? And now I'm going to adjust my trigger so that they cross, so that the yellow is at my reference point. Doesn't matter which grid you choose there, but we just want to choose a reference point. Okay, so I'm going to choose this reference point, and now I'm going to count divisions. So I have one full division, and then it looks like between 0.2 and 0.4, so I'll call it about 0.3. Okay, so I've got 1.3. So 1.3 divisions in the horizontal direction times 250 microseconds per division. Now this is microseconds. Okay, so we're looking below the line there, if you can see that. 1.3 divisions times 250 microseconds per division. And so 1.3 divisions times 250 microseconds per division gives us 325 microseconds. So what we're saying is that the voltage across the capacitor is 325 microseconds. So, you know, we'll make that like a negative sign there. 320 microseconds behind the supply voltage. Okay, and so if we want to calculate our phase angle, then our phase angle would be it's taking 10 milliseconds for a complete cycle. Okay, so it's taken 10 milliseconds for a complete cycle, and a complete cycle is 360 degrees. And we're going to multiply that times 325 microseconds. Alright, so here's our calculation. So it takes one complete cycle is 360 degrees, which is taking 10 milliseconds. And the voltage across the capacitor is 325 microseconds. This is microseconds behind the supply voltage. So we take 325 microseconds times 360 degrees divided by 10 milliseconds, and that gives us an angle of 11.7 degrees. Now, the angle we actually calculated was about -8 degrees. So we're a little bit off. And there's a couple of reasons we could be off. Number one is we're using the face plate value of the capacitor of 0.22. The capacitors often are, they tend to vary a lot more than resistors. So it could be that our capacitor is a little bit off, and the other reason we can be off is just because we're trying to read these off of an oscilloscope. They're going to it's hard to read very accurately, so we're off by about 3 to 4 degrees right now, which is not too bad. Like I say, part of that might be because our capacitor might be a little bit off in value. Okay. And so, but that was for just the one, that was for the frequency of 100 hertz. All right, so let's go ahead and dial it up to our 723. So we calculated that critical frequency where the capacitive reactance was exactly equal to the resistance was at 723 hertz. And at that point, we would have 3.53 volts. Okay, so the peak to peak of that would be 3.53 times the square root of 2 times 2. So the peak to peak would be 10 volts. Okay, so the peak to peak would be 10 volts, and the angle would be minus 45 degrees, right? If we round that up to 3 digits, it would be 45.0 degrees. So, so if I crank my frequency up to 723, okay, so I'm going to crank my frequency up to 723 hertz. And so now it looks like the voltage across the capacitor is bigger than the supply voltage. But remember, your voltage is per division. So the yellow is 2 volts per division, but the blue is actually set to 1 volt per division right now. So if we set them both to the same volts per division, you can see that it is significantly less than that, than the yellow. All right, but if if I set it to 1 volt per division, it's cutting off on the screen. So I'm going to set it to 2 volts per division, and I'm going to, when I'm trying to measure peak to peak values, it's a lot of times it's easier if we if you get more waveforms to read the peak to peak. So I'm going to get more waveforms here, and I'm just going to raise this up so that this waveform is starting. In this case, I chose the second line, so it's starting on the second line, and then I'm going to line it up here for the center. So I'm going to count how many divisions. So it's 1, 2, 3, 4 complete. And then it looks like about 4.5. So it looks to be about 4.5 divisions in the vertical times 2 volts per division. Okay, and so our voltage then is about 9 volts per division. 9 volts peak to peak. I'm sorry, not per division, but 9 volts peak to peak. Okay. So again, part of the reason for that might be that our capacitor, I should have measured the capacitor before starting this video. The capacitance may be a little bit off. So we should be exactly at 10 volts peak to peak, and we're actually reading 9 volts peak to peak. So we're a little bit off. Let's check our angle. Okay, so now I'm going to turn back on channel 1. And again, I'm going to adjust. Now, I don't have to recalculate. Actually, I guess I do have to recalculate my period because I've changed my frequency. So I've changed the frequency, so I need to recalculate the period. So I'm going to put the yellow, turn off channel 2 for a minute. You just press the channel number, and it'll turn off. And so I'm going to line this up. So I've lined this up at a grid, and I'm going to count 1 complete cycle. So that's 1, 2, 3, 4, 5. So I'm going to call it about 5.5. Okay. So that's about 5.5 divisions times, and I'm at 250 microseconds per division. Okay, because remember, I've changed my frequency now, so I'm going to recalculate that. Alright, so I've calculated my period was 5.5 divisions times 250 microseconds per division, which gave me a period of 1.375 milliseconds. And so if you take the reciprocal of that, then you get 727 hertz, which, you know, according to my function generator, I'm at 723. So you see that that read fairly accurately in the horizontal direction. Okay, so so that worked very well. So I'm going to turn back channel 2, and you can see that there's a huge difference now between where the yellow starts and the blue starts. Okay, so it's a larger distance, so you can see that that angle has increased dramatically. So again, what I'm going to do is I'm going to increase the magnitude of the verticals to make them cross, to make them so they're going more vertical up and down, so I can read it a little bit more accurately. And then I'm going to maybe change my time a little bit, and I'm going to drag them over here to a starting point. So I'm going to put this at the starting point right there. And now I'm going to read divisions. So we've got about 1.9 divisions on here. 1.9 divisions times 100 microseconds. So we have 1.9 divisions times 100 microseconds, which of course, microseconds per division. So the divisions cancel, and we're left with about 190 microseconds delay. Okay, so that the voltage of the capacitor, which is blue, the voltage of the capacitor is about 190 microseconds behind the voltage of the supply, the reference voltage. So when we calculate then our phase shift, we have our 190 microseconds times 360 degrees divided by 1375 microseconds. So remember, one complete cycle was taking 1375 microseconds. The microseconds cancel out, and we're left with degrees. So we're at 49.7 degrees. So our phase shift is negative, and it's a negative phase shift, right? Because the voltage across the capacitor is behind or to the right of our reference, which is the supply voltage. And so it's a negative 49.7 degrees. So that's our phase shift at this frequency. So again, we were expecting minus 45 degrees, but you know, the capacitor is maybe a little bit off here. I'll have to try and measure that and see what that actually is. But that would be the biggest reason for the difference. Also, just trying to measure, you can only be so accurate measuring fractions of a division there on the oscilloscope. So minus 49. We were expecting 45, so we're off less than 5 degrees. So that's not too bad for an experimental result here. Alright, so now we're going to go ahead, I'm going to go ahead and just crank this thing up. So I'm going to crank my function generator up to 10,000. So I'm going to use the enter number option again. So I'm going to hit enter number. And I'm going to put in 10, so use the green numbers there. So I'm going to put 10.0, and then I'm going to choose the kilohertz option. So there's my 10,000 hertz. And again, you can see the blue voltage has dropped significantly in magnitude, okay, because of the new frequency. And you know, you can see a lot more sine waves showing up on the screen there. And so we want to measure the period of a sine wave. So again, I'm going to kind of get this so I can get one complete sine wave on here. And I'm going to go ahead and turn off channel 2 for a little bit. And I'm just going to line up one complete sine wave. I'm going to see if I can get one complete sine wave on here. Okay, and it's really hard because it's actually going to be right at the very edge. But remember, this is supposed to be 10 kilohertz. Okay, so it's actually a nice round value, 10 kilohertz, right? So I have, if you count there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So there's 10 divisions on the scope, and it's basically going and using those 10 divisions. So we have 10 divisions times 10 microseconds per division, which of course then is going to be 100 microseconds, which is the period. So the period is 10 divisions times 10 microseconds per division, so we end up with 100 microseconds, and so therefore our frequency is 1 over 100 microseconds, which should be 10 kilohertz. Okay, so that's just to verify that we can read the frequency on the oscilloscope. All right, so once we've done that, I can turn on channel 2, and I just want to measure my voltage. Okay, and again, the voltage here, I'm going to turn off channel 1 for a minute, and I would just want to read the peak-to-peak value of this. Okay, so I might adjust this a little bit and read the peak-to-peak value. I'm on 200 millivolts, so that's 1, 2, 3, 4. So the peak-to-peak is about 4 divisions times 200 millivolts per division, which is about 0.8 volts. Okay, so it's about 0.8 volts, the magnitude. Now that, remember, that magnitude is peak to peak. This is the peak to peak value, and so we need to divide this by 2 square root of 2 to get the RMS. And so our RMS voltage then is about 0.283 volts RMS. Okay, and so that's what we're reading on the screen here. Okay, now to read the magnitude, and one thing I kind of forgot to do actually when I was doing that before is if you do adjust your voltage, where it starts at, it's ground reference. Remember, there's this little tag here which shows you, lines it up. You need to make sure that they are lined up right on top of each other, okay, on that center line when you're trying to measure time. Okay, when you're measuring peak to peak, it's fine to shift it, but you need to remember to adjust it when you're trying to measure time. So again, here I'm going to try to measure time here. So you can see how far behind the blue is now. And again, I'm going to like increase the magnitude of these. Okay, and you can see like this blue waveform is kind of wider and jumping around a little bit more. That's because of the noise, because it's such a small voltage now. And so again, I'm going to line this up so that's right there. So the yellow is right at the start of a division. And actually I'm going to turn off channel 2 for a minute. I need to calculate, oh wait, no, I did calculate the period of the waveform. All right, we calculated the period of the waveform, so we've got that. And so we're going to measure this now. So I'm at 10 microseconds per division, and I'm going to count my divisions. So I have 1, 2, I'm going to call it about 2.3. It's actually a little bit more than that. You know, you might even call it 2.35 if you wanted to be a little more accurate. So we're going to say that the angle remember the period of our waveform, one complete cycle was 100 microseconds. And so we just looked there and we calculated 2.35 divisions between channel 1, which was my supply, and channel 2, the blue, which is the voltage across the capacitor. And so it was 2.35 divisions in time times 10 microseconds per division was the setting of time. And so we multiply that and we get 23.5 microseconds. And so if we then calculate the actual phase angle, we're going to have 23.5 microseconds divided, multiplied times 360 degrees divided by 100 microseconds. Microseconds cancel. Okay. So the microseconds cancel, and we are left with 84.6 degrees. So that is our phase shift, 84.6 degrees. So there is how we can use the oscilloscope to read values, both amplitudes and time and phase shift on oscilloscopes. Okay. All right. So again, the blue is the voltage across the capacitor, and the voltage across the capacitor, if I set them both to 2 volts per division, right, you can see how the voltage across the capacitor, the capacitor is dropping very little of the voltage now. It's all dropping across the resistor. So one more thing that I want to kind of show you, I discussed it at the beginning of the video, but I just want to show you this ground. If I take in my circuit, let me see if I can get this other camera on the circuit for a minute. Okay. And if I take in this circuit here, and if I wanted to measure the voltage across the resistor, okay, and so if I was to try to put the ground up here and put this here, then what you're going to notice is on the sine wave, they're both right on top of each other because I've shorted out the capacitor. And so what I'm looking at here is just the supply voltage, basically. Shorting out the capacitance within the circuit because I've threw in that ground wire there. Okay, so you need to be careful with that. Okay, so because the scopes have the ground is connected internally. So once you ground, see, if I don't even need to connect this ground because it's already connected down here. The ground is connected. Not sure how well you're catching that on the video, but this ground here on for the second channel I don't even have connected because I have the ground for the first channel connected. So this second ground, it's useful to kind of help minimize noise in your signal on the scope, but that's all it can do for you. You don't even need to connect the second ground on the probes. You just have to connect one because they're connected internally. But if the signal's noisy, you want to hook up the other one. It'll help give the noise a chance to get to ground. But only one ground is needed because the grounds in channel 1 and channel 2 are connected internally in the oscilloscope. Okay, so I wanted to see what the actual value of this capacitance is. So I've got my digital multimeter here. A lot of DMMs actually give you a capacitance reading ability on here. So this particular meter can read capacitance. And so remember this, the face value of this said it was going to be 2.2, but when I hook it up here, we see that it's actually, I can get a good contact here, it's reading about 2.38, about 2.4. Okay, so it's reading about 2.4, or even a little over 2.4, I guess, once I hold it there. Okay, let's see. So so the value is fluctuating there a little bit. Okay, so actually as I connect it, it's actually going up higher. Let's see. So when I first connect it is probably the most accurate reading. So when you first connect it in there, it's reading about 2.4 0.24 instead of 0.22, which is what it was rated at. And so it's pretty close, but it is a little bit off. So when I calculated the angle then, using for at 723, let's find my sheet here, at 723 hertz. So when we calculate that, we end up finding, using that, using like about 0.24 instead of 0.22 microfarads, we end up finding that the phase shift angle is about minus 47, 48 degrees, and the peak-to-peak value, and that's at the 723 hertz. So at the 723 hertz, it was 9.5 volts peak to peak, which is about 3.38 volts RMS, and an angle of about minus 47 or 48 degrees, which is a little closer to what we calculated. So really, before you start using capacitors, you should really never use the face value of those. You should measure those values and then use that measured value.